Welcome back. The objective of this video is to generate exponential functions from geometric sequences. We have seen that when output values of a function change at a constant rate, the function is linear. Now we're going to look at what happens when the output values change proportionately. So that means we're going to have a fraction or a ratio. When your sequence is geometric, the rate of change will increase or decrease as the value of n increases. In example 8, we want to use the graph of the sequence shown at the right to complete the following table. So in our graph, we can see here that our changes in y are decreasing as our x's are increasing at the same rate. So our x's are increasing by 1s, but our y's are decreasing at a much greater rate. Well, we want to find out what that ratio is. So they ask us to complete the table below and then find the common ratio and write the explicit rule. Well, let's take a look. If we're going to have a consistent ratio here, we can take a look at our two outputs for y and divide them and come up with that ratio, 32/64, which is 1/2. So it looks like our common ratio would be 1/2. So that means 3 would correspond to 16, and then half of 16 is 8, and half of 8 is 4, half of 4 is 2, half of 2 is 1, and that does seem to correspond with the values in our graph. So our r is 1/2, and it appears that a to the n equals 64 times 1/2 raised to the n minus 1. So our first term gives us a value of 64. So a sub 1 equals 64 times 1/2 to the 1 minus 1. So we have 1/2 to the 0 power, and our b value is 1/2, and our a value is 64. Another way to look at that, we could also look at that as a to the n equals 128 times 1/2 to the n. We probably won't do that very often, but that's one of the options out there. And then it says, use the information from part B to write an exponential function that corresponds to the nth term. So we're just going to put this in function notation. F of n equals 64 times 1/2 all raised to the n minus 1, or f of n equals 128 times 1/2, our ratio raised to the nth power. In example 9, we're given a geometric sequence where a sub 1 equals 144, a sub 3 equals 36. State the domain and range of the sequence. We need to find out what our ratio is here, and we can calculate the second one by doing the square root of the product of these. So we can figure out a sub 2 is equal to the square root of 144 times 36. I'm not going to multiply those together. I can separate those. I can do the square root of 144 times the square root of 36, which is equal to 12 times 6, which is 72. So a sub 2 is equal to 72. So now I know what that is. I can calculate my ratio. So now my ratio is 72 over 144, which is equal to 36 over 72. My ratio is 1/2 again. All ratios aren't 1/2, but they are pretty easy to work with in sample problems. So I can do half of 36 is 18, half of 18 is 9, half of 9 is 9/2, half of 9/2 is 9/4. So my domain is my x values. In this particular table, just 1, 2, 3, 4, 5, 6, and 7. and our y values is also our range, which is 144, 72, 36. I'm going to run out of space. 18, 9, 9 halves, and 9 fourths. In example 10, we want to write an exponential function whose domain is all real numbers that will contain the domain of this. So we're going to use example 9, and we're going to write this in function form. That includes all x's and all y's. So I would say that's f of n equals 144 times our ratio 1/2 to the n minus 1. Or as we did previously, double 144, we get 288, and that could be 1/2 just raised to the n power. So what we've been doing in the last couple problems is we've been writing an explicit formula for the nth term of a geometric sequence. And it can be modeled using an exponential or growth or decay formula is really what we're doing. So we're given a sequence of 3, 6, 12, 24, 48, 96. Find an explicit formula in both subscript notation and function notation. So our first term is 3, our second term is 6, 12, 24, 48, 96, and so forth. So we can see here that our y's are doubling. So we know that our r here, our r is equal to 6 over 3, which is equal to 12 over 6. So our r is equal to 2. Or our ratio is equal to 2. And when we raise 2 to the 0 power, it becomes 1. But our y value is 3, so our function in subscript notation is 3 times 2 to the n minus 1. And in function notation, f of n equals 3 times 2 to the n minus 1. Our subscript notation, a sub 2, 3, 4, finish our table, a sub 5, a sub 6, a sub n, and our function notation, f of 2, f of 3, f of 4, etc. So there's the completed table for you. In sample 12, we're given the explicit formula for the sequence a sub n equals 6 times 1/2 to the n minus 1. So we've got a decay formula. Our ratio is 1 over 2. So each subsequent value is going to be half of the previous one. We want to write the first 6 terms of the sequence. So let's go ahead and do those. And that means the first term we put a sub 1 and a sub 2 and a sub 3 and so forth. So that would be 6 times 1/2 to the 1 minus 1, and 6 times 1/2 to the 2 minus 1, and 6 to the 1/2 times 3 minus 1. So our first term is 6, our second term is 3, our third term is 3/2, and so forth. So I did the formula for the first 3 and wrote those down. We have 6, 3, 3/2. Half of 3/2 is 3/4, and half of 3/4 is 3/8, and half of 3/8 is 3/16. So those are the first 6 terms. Find the a sub 0 term of the sequence and support with work. So we could do a sub 0 equals 6 times 1/2 to the 0 minus 1. and putting that, so that would be 6 times 1/2 all raised to the -1 power, which is 6 times 2, or 12.